talk about matrix inverses. First, let's review some properties of left multiplication by matrices. Say that V is the collection of n-dimensional vectors and W is the collection of m-dimensional vectors. We'll denote beta and gamma as the standard bases for these vector spaces, respectively. Given any m by n matrix A, we can define the linear transformation L sub A as multiplication by our matrix A. Quite literally, this is the left multiplication transformation. Observe that because we're dealing with the standard bases, the matrix representation of L sub A is just the original m by n matrix A. We'll define the rank of this m by n matrix A as the rank of this left multiplication transformation. That is, it's simply the dimension of the range. Again, let A be an m by n matrix, and let's say that B is obtained from A by performing an elementary operation. If this were a row operation, then we can simply write B as E times A, where E is some elementary m by m matrix. Similarly, if this were a column operation, we could write B as A times E for some elementary n by n matrix E. Finally, our elementary matrices E are invertible. Let's say that A is again an m by n matrix. Then A is invertible if and only if both m equals n and the rank of A equals n. M here is the number of rows and n is the number of columns. Let's say that A is the matrix representation of some linear transformation T with respect to some bases beta and gamma. Then the rank of T is equal to the rank of our matrix A. Finally, let's say that B is P times A times Q for some invertible m by m matrix P and some invertible n by n matrix Q. Then the rank of A equals the rank of B. In particular, similar matrices have the same rank. Two matrices A and B are similar if we can write our P as the inverse of Q. Next, elementary matrices on a matrix are rank preserving. Here remember that we're simply multiplying either on the left or on the right by some elementary matrix E. We're going to use all of this to discuss some properties of the ranks of matrices. Let's start by presenting a result based on several homework problems. Let's say that A is again an m by n matrix. Remember that m is the number of rows and n is the number of columns. We'll denote R as the rank of this matrix. First, we see that R is never greater than m or n. R is less than or equal to the number of rows, and it is less than or equal to the number of columns. Next, there exists an invertible m by m matrix B and an invertible n by n matrix C, such that B times A times C is the matrix you see here on your screen. Essentially, we have R, ones, along what looks like the main diagonal, and zeros everywhere else. This means if we can place our matrix A in this form for some B and C, then it's a matter of just counting the number of non-zero entries, the number of ones here along the diagonal. Finally, both A and its transpose have the same rank. As a remark, our m by n matrix D can be found through elementary operations. Later we'll see that this is what's called the echelon form of the matrix A. Before we go any further, let's try to discuss an example. Let's consider the matrix you see here on your screen. This is a 2 by 3 matrix. That is, it has 2 rows and 3 columns. Notice that the rank R must be less than or equal to 2 because R is never greater than the number of rows or the number of columns. Previously, we found a matrix D, which is B times A times C, in terms of matrices B and C that you see here on your screen. Notice that B is an m by m matrix, where m is 2, and C is an n by n matrix, where n is 3. Both B and C are invertible matrices because we can explicitly write their inverses, as you see here on the screen. Hence, the rank of A must be equal to the rank of D, this number R. Finally, we see that R must be 2 because looking at the matrix D, we see that we actually do have a 2 by 2 identity matrix sitting along the main diagonal. Now we turn to the proof of the theorem. This proof will involve quite a bit of notation, so we introduce the diagram that you see here on your screen to help keep track of the various concepts. The idea will be we start with standard bases beta and gamma, and we're going to construct new bases, beta prime that you see at the upper left and gamma prime you see at the upper right. These two new bases will help us to introduce the matrices C and B as in the theorem. Let's consider a linear transformation L sub A that comes from left multiplication by A. If we let beta and gamma be the standard bases, then remember that our matrix A can be recovered as the matrix representation of this left multiplication by A. We know that the range of left multiplication is that vector space spanned by the columns of A. Since we have a spanning set, let's perhaps change the notation if necessary and just look at the first R elements, because R is the dimension of our space. So by looking at the first R elements in the spanning set, we do indeed have a basis, a linearly independent set that spans the space. The dimension of left multiplication by A, the range of this multiplication, is what we defined as R, but because the range is a subspace of the codomain W, we see that R has to be less than or equal to M. Similarly, the dimension theorem says that the dimension of the range has to be less than or equal to the sum of the dimension of the range plus the dimension of the null space. So we see that R must be less than or equal to N, the dimension of the domain V. So this shows the very first statement. Now we saw before that the first R columns of our matrix A form a linearly independent set. They actually form a basis. So let's express the remaining N minus R columns of A as linear combinations of the first R columns. We'll denote beta prime in the following way. First, we'll choose the first R basis vectors because remember that the image of those corresponds to the basis vectors for our range. We'll now look at the last N minus R vectors that we define in a rather strange way. We're defining it simply so that the image of the last N minus R vectors is 0. So the first R actually give us back the range of L of A, whereas the last R lie in the kernel of the map. They generate the null space. Since we have a collection of vectors that forms a basis for the range, this is our set S, we know from a previous homework set that we can extend this basis to a basis of the codomain W. This new basis we will call gamma prime. Now it's a matter of realizing that beta we chose in a very clever way, gamma prime we chose in another clever way, and so we finally find this matrix D, which is what we desired in the first place. We'll discuss more properties of this matrix D in the breakout rooms as well as the homework assignment. By staring at the diagram that I showed at the very start of the proof, we actually see that our D can be expressed as a product B times A times C by simply looking at how things factor in the various compositions. This now shows the second statement. As for the third, we really need to stare at the idea that the rank of D is the rank of A. Again, B and C are invertible matrices. Now note that if we take the transpose, then we see that for our matrix D, we can compute the rank by looking at the diagonal where the first R terms are equal to 1. For the transpose, we find the same concept, namely that we have a matrix where the first R elements along the diagonal are equal to 1. So by simply counting, we see that the rank of D transpose is equal to the rank of D, which is the number of these non-zero entries, which is R. However, because the matrices B transpose and C transpose are also still invertible, we see that the rank of A, which is the rank of D, which is the rank of D transpose, must be equal to the rank of A transpose. This completes the proof of the theorem. Let's use all of this to talk about compositions of functions once again. We'll end today by discussing a few results that will allow us to say a little bit more about the ranks of matrices. Let's say that A is an M by N matrix and B is a P by M matrix. Then we can multiply B times A, and the theorem states that the rank of the matrix B times A is less than or equal to the rank of A and the rank of B. Let's say that T and U are linear transformations. Then the rank of the composition U circle T is less than or equal to the rank of T and is less than or equal to the rank of U. Let's show the first statement. The idea will be to look at the following compositions of linear transformations. First, we'll multiply by A, then we'll multiply by B. This, of course, corresponds exactly to multiplying by B times A. We, of course, remember, by definition, that the rank of B times A is the dimension of the range of left multiplication by B times A. However, this diagram here shows that the range of multiplication of B times A must be contained in the range of multiplication by B. Therefore, the rank of B times A must be less than or equal to the rank of B. Now let's take a look at the transpose. The rank of B times A is the rank of B times A transpose, but B times A transpose is A transpose times B transpose. Now using the previous result, we see that the rank of B times A is less than or equal to the rank of A transpose, but we know that this is simply the rank of A. This shows the first statement. We'll show now the second statement. Let's let T and U be transformations between two finite dimensional vector spaces. We're going to choose bases beta for V, gamma for W, and alpha for Z, and then define a matrix representation A for our transformation T, and a matrix representation B for our transformation U. Now, we simply use the previous results to understand that the rank of the composition U circle T is at most the rank of T and is at most the rank of U. This completes the proof. Thanks very much for watching.